Intro chemistry, preparation of acetyl salicylic acid, commonly known as aspirin. Here's the reaction equation. Salicylic acid reacts with acetic anhydride, which is anhydrous acetic acid. In the presence of an acid catalyst, we will use phosphoric acid, producing acetyl salicylic acid and acetic acid byproduct. For expedience, I may refer to salicylic acid simply as SA and acetyl salicylic acid as ASA or aspirin. It's interesting that salicylic acid occurs naturally in the bark of willow trees, and willow bark tea has been used for centuries as a pain reliever. An ancient Egyptian papyrus medical text refers to willow bark as a pain reliever. In 1899, a young German chemist, Felix Hoffmann, working for the Bayer Chemical Company, obtained a patent for the process of synthesizing acetyl salicylic acid, which was then called aspirin. And we're going to reproduce that synthesis today. Now, like many organic reactions, this reaction does not go to completion. There will be some byproduct acetic acid, and so to obtain a pure product, we'll need to carry out recrystallization. So let's get started. We start by weighing about 3 grams of salicylic acid. I've already got that quantity in the weigh boat. Anytime you're going to transfer a solid, make sure you use a powder funnel. That way the solid gets into the flask, not on the balance and not on the lip of the flask. You want to record this mass. .95 grams. Next, we're going to add about 6 mils of acetic anhydride. Notice again, we're going to use a powder funnel to make sure that the liquid gets into the flask and not on the lip of the flask. Now, acetic anhydride is added in excess, so I don't need to know the exact quantity. Our next reagent is a catalyst, conc phosphoric acid. When you weigh a catalyst, you don't need an exact quantity. Here it is, conc phosphoric. So 5 to 8 drops should be good. And anytime you're going to transfer with a Pasteur pipette, make sure that your flasks are as close as possible, like this, so you minimize spilling. And if I had 2 hands free, I'd hold the 2 lips right close together. Next, we'll put our mag stir bar in and transfer to a hot water bath. We'll suspend this in the hot water bath so the mixture is immersed. We're going to heat that to about 90 degrees Celsius. Once we get it at 90, we'll hold it there for at least 15 minutes to make sure the reaction reaches equilibrium. We use an alcohol thermometer to measure the temperature of the water bath. You'll notice that I covered the flask with a powder funnel. That's to minimize the amount of solvent that evaporates. We don't want to lose solvent during the reaction. We'll heat it to 90 degrees C, and here it's been at 90 degrees C for at least 15 minutes. So we'll dismantle it and let it cool to room temperature. Solution looks clear, that's a good sign. We're going to add about 40 mils of water, and that'll cause the ASA to come out of solution.
Now ASA is a solid at and near room temperature, but what's come out of solution here is actually another liquid. That is called oiling out. It's not a good thing. We can't filter our solid if it's not a solid. We'll add some crushed ice to see if that helps, but if that doesn't work, what we have to do is simply scratch the bottom of the flask with a glass stir rod, and that creates a few particles which serve as nuclei for crystallization to begin on. No solids yet. No, just an emulsion of two oils. We have to get it out of solution. Let's put it in the ice bath, and I'll keep scratching the bottom of the flask. Well, after about 10 minutes of cooling and scratching, we do have a healthy crop of crystals. Let's recover that mag stir bar. I should have really taken it out before crystallizing. I notice I have some ASA on it. I'll try and rinse it off, but it doesn't want to come off, so we'll catch that later during the recrystallization. Now we're going to filter this. We don't need the mass of the paper because we're going to just redissolve our solid in any case. Seat the paper so it sits flat. No solids get under it. Remember that when you pour a slurry onto a filter paper, pour as quickly as possible without spilling so you cover the entire surface of the paper with an even bed of solids. You don't want a cone in the middle. That won't wash well. Likewise with your rinses, try and cover the entire surface if you can. We're trying to wash out the residual acetic acid here. This is 20 mils of cold water. We will lose some ASA in the process because it has some solubility, but that is the cost of purification. At this step, we'll transfer our crude product to a beaker, add 30 mils of water, and heat it to near boiling. Now, if there are any undissolved crystals, we want to put those in solution by adding small quantities, just small squirts of distilled water, keeping it hot. And once those final crystals go into solution, we know that we have a saturated solution, hot, and when it cools slowly, we should be able to grow some pure crystals of our ASA product. Alright, I'm going to remember to fetch the mag stir bar out before crystallization occurs this time. And I'll cover that with a watch glass to prevent evaporation and leave it sit undisturbed while it cools to room temperature. So it sat at room temperature for a bit, and now we have some crystals. We'll maximize our yield by putting that in an ice bath for about 10 minutes. And this is a good time to weigh up our beaker and filter paper for our final mass. Now I see the display on the balance is not showing well on the camera, but I'll read you the mass. It's 66.40 grams. You want to record that. Alright, so ready for the final filtration. Here's our pre-weighed filter paper. Seat that. Our solids have really congealed. I'm going to have to stir that up a bit with a stir rod before I can filter it. So here's the final filtration and wash. And finally we'll transfer our pure solid and filter paper into the pre-weighed beaker. We'll need to let it dry overnight before we can get the final mass. So here, the final mass of our dried product. You want to record this, 69.14 grams. Here's the final product. It looks clean, white, crystals are well formed. It certainly looks pure. So the last step of our experiment is to go back to the procedure, look at how to record your data and results and do your calculations.
So to finish up this experiment, please record your results in a table that's set up the same as the one that's shown here. Here's a sample data set that you can use to follow. So in this example, let's say you had an initial mass of 3.03 grams of salicylic acid and you recovered 3.2 grams of ASA. How do you calculate the theoretical yield and the percent recovery? If you follow down here, work below a balanced equation. Here's the mass of salicylic acid divided by the molar mass gives us moles. Grams divided by grams per mole is moles. From the stoichiometry of the equation, 1 mole of SA produces 1 mole of ASA. So similarly, 0.219 moles of SA will produce 0.219 moles of ASA. How do we get grams from that? Well, multiply moles times grams per mole gives us grams. So 0.219 moles of ASA times its molar mass will give us the theoretical mass of ASA. That's not what you recovered, that's what you calculate. Then to calculate the percentage yield or percent recovery, take the actual yield, 3.20 grams in this example, divided by the theoretical yield, 3.95 grams times 100 is 81%. And that concludes our experiment for the preparation of aspirin.